we're going to review really quickly inverse functions. I know we've been talking about them as far as e to the x and natural log of x are concerned, but we're just going to say in general, we're going to talk about any set of inverse functions, f and f inverse. So let's say we have a domain value of x and we're going to plug it into this value or this function that manipulates it somehow, this function f, and it's going to yield us a range value we're going to call y. If we pick that range value of y up and we plug it into the function g of x that does some sort of mathematical operation, if g maps us back to the original domain value we started with, it tells us that f and g have this relationship, that g is the inverse of f and f will be the inverse of g. It tells us that the range of f will become the domain of g and the range of g came from the domain of f. Recall that. Also, really quickly, watch your notation. For any mathematician, if they see a superscript of -1, that does not mean reciprocal to them. That means inverse. So in function notation, never use the superscript -1 to talk about the reciprocal of the function. Graphically, we remember that inverses are reflections of one another in the plane over the line y equals x. So one function undoes or reverses what the other one did. That is, if we compose them in either direction, we get mapped back to the original value that we started with. Analytically, if we are asked to find the inverse function, here are the steps that you go through analytically. Now realize on the BC exam you won't be asked to do this. This is a pre-calculus concept, not a calculus concept, but it's something that would be good for algebra practice. So if we're given a function f of x, which is, some manipulation on the variable x, the very first thing we do is drop f of x and replace it with y, and then just copy down everything on the other side of the equal sign. Then we switch or we swap our x's and our y's. Everything that's written over here in x, now we're going to write as y, and we're going to replace that y with x. Then we're going to take this relationship and we're going to solve it for y and put it in terms of x. And once we've done that, we've actually found the inverse function to f that we started with. So there's analytically how we would find the inverse function, if you'll remember that from pre-calculus. Now let's begin our discussion about the derivatives of a set of inverse functions. If we have f and we have f inverse, we're going to call this function f of x. We're going to call this function f inverse of x. If the function f contains the point AB, we are guaranteed that perpendicularly over the line y equals x in the plane, its inverse function must contain the point BA. In other words, if I put an x value of a into the function f, it's going to yield me a y value of b. And if I take that same value of b and plug it into the inverse function, I'm guaranteed that it will give me a y value of a. They undo each other, these inverse operations. So let's look at the derivatives, or the slope of the tangent lines, for a function f and its inverse function f inverse. So the slope of the line f prime at x equal a has a relationship. It's not a direct relationship, but it has a relationship with the derivative of its inverse function through b, and it is a reciprocal relationship. The slope of the tangent line through a on f is the reciprocal of the slope of the tangent line through f inverse at b, and the same is true for f inverse prime at b is going to equal 1 over f prime of a. Now notice these are different input values, so that's the kind of the tricky part to this. Let's work a couple of examples really quickly, and then we'll do some homework problems when you get to class, and you'll get a better idea of how to do this. So here's an example. Given the function f of x, without actually analytically finding f inverse, they want us to determine f inverse prime at x equal 1. Now this gives me some information. This tells me b equals 1. It tells me that there was some a value that we plugged into the function f, and the result of that was 1. So we have the point in the plane A1, and what we need, f inverse prime at 1 is going to have to equal 1 over f prime at that a value. So we're going to need some things. We need the derivative function. We need to figure out what a is. This helps us find a. F of a is going to equal 1. So we're going to take our function and set it equal to 1. And then we'll evaluate and find what f inverse prime at 1 is. So step 1 is let's find the derivative function. This is a quotient, so it's going to require the quotient rule. That's bottom d top minus top d bottom all over bottom quantity squared. We could clean that up a little bit. That's 5 minus 10x plus 10x over the quantity 1 minus 2x squared. So all cleaned up, our derivative function in x is 5 over the quantity 1 minus 2x squared. Now we need to find a, because eventually, or what we're after, is evaluating f prime at that a value. So let's go back up and let's pick up our function f of x, and we want to set that equal to 1. And that x value, whatever x value makes this a true statement, is a. This is how we're going to find a. So I'm going to multiply both sides by 1 minus 2x. I can add 2x to both sides, and it turns out that x, or that a value that we're after, is 1/7. So let's see, I think I have some space over here. So f prime of 1/7 equals 5 over the quantity 1 minus 2 times 1/7 squared. Quantity squared. Okay, so f prime of 1/7 is 5 over 1 minus 2/7. That's 7/7 minus 2/7, so that is 5/7 quantity squared. So we have 5 over 1 over 25 over 49, and so that cleans up to 5 over 1 times 49 over 25. So that's 49/5, and that is f prime of a. So f inverse prime at 1, I'll just sneak this in right here, is 1 over 49/5, or it is 5/49. So not quite as straightforward, as if it was f inverse prime at a equals 1 over f prime at a, but you get the idea. Let's work this one final example. Here's another function, f of x, and they want us to find f inverse prime at 4. Again, we have some point on f that is a of 4. So we're going to take our f function and we're going to set it equal to 4, and we're going to find out what x is. So 2x to the 5th plus x cubed minus 3 equals 0. And we could find out what that is. You can use your calculator, whatever you want to do, but we find out that x is 1. So for us, a equals 1. So this one's a little bit easier even than the last one. So it has to be true that f inverse prime at 4 is 1 over f prime evaluated at 1. So let's see what f prime is. F prime of x is 10x to the 4th plus 3x squared. So we're going to put that down here and evaluate it at 1. 10 times 1 to the 4th plus 3 times 1 squared is 1/13. So it sounds kind of complicated, and I know it seems very involved, but if you'll just remember that the input on the inverse function is the output on the original function. And so you just have to pay attention to what you're looking for and how you get there. So luckily this is a concept that is not tested very often on the actual BC exam. I've seen many released multiple choice questions and free response questions, and in all the years that I've been doing this, I have seen one and only one question that directly tested this concept. So we don't need to hit this out of the ballpark. We are going to do some homework problems over it, but there's much more as far as transcendental functions are concerned that we need to know how to do, and how to do very well and very concisely, and this just isn't one of them. But I do cover it every year because there is a possibility there might be one multiple choice question over it, and if you happen to remember, at least you can do that problem. So come to class next time and we'll do some homework problems over derivatives of inverse functions.